Now let's continue exploring the possibilities and the workflows with working with pops. So I'm going to go up, I'm going to hide this geometry container, and let's create a new one. I'm going to create type geometry, and let's call this pop demo. I'm going to dive inside. Let's create a grid, and I'm going to make the grid 1 by 1 again. I'm also going to position it differently. I'm going to say it's facing this plane, and I'll just apply a transform to pull it up. Enter in the 3D view, and let's say something like this. Okay, that's cool. Hit escape to lose the gizmo. One thing that you can keep in mind, and it's really a very common workflow, is to take advantage of the fact that your particles, when you're generating particles from a surface, the particles have the ability to inherit the point attributes from that surface. So it's pretty common for us to, for instance, apply normals to this. Apply normals, let's make it visible. So now we have normals. Remember, it has to be on a point attribute in order to be passed through to the particles. So we have these normals. And what we can do is, for instance, convert these normals into velocity by using a point for angle. And we can say that our velocity is equal to the normal. And now we'll have velocity on these points. If we check the geometry spreadsheet, we'll see we have normals and velocity, and these are pretty much the same. So I'll type here convert n to v. Now if we fit this into a pop network, let me hide the normals. You'll see that the particles are start to move right away. And the reason for that is, if you dive inside, you'll see that here on the pop source, on the attributes, it's inheriting all the attributes by default, and initial velocity is use initial velocity. That's why we get that movement. Of course, this makes it very easy for us to control how the particles are being emitted in terms of the speed they have and the direction. For instance, if we go here up to the normals, let's say we create a point pop. Let's make the normals visible, and we'll dive inside, and let's add some noise to the normals. So we can create an AA noise. This noise is interesting because it can take, instead of taking a vector, it can take a quaternion, which will be a 4-element vector, where you can mix the position and the time variables. So you can convert, if we type vector, you can convert the vector to a vector 4, and you can mix the position with the time. It'll convert it into a vector 4, and if you connect this to the anti-aliased noise, it automatically adjusts the signature from 3D input to a 4D input. And as you can see, you have an extra. Instead of having just 3 elements on the frequency and the offset, you have 4. This is X, Y, Z, and the 4th element, which in our case is going to be time. Let's just increase this to 2, 2, 2, 2. And let's make sure that we're outputting a vector. And let's connect it to normals, and we'll see what we get. Let me turn on wireframe. Okay, so these are our normals. We can normalize them, and we should. So let's apply a normalize. Okay, just so we're sure that we have the right length. And then what we can do is add these vectors to the normals that we already have. We grab the normals that we have, and then we mix them with these. We should normalize these as well. But now, as you can see, we have an interesting pattern, a variation on the noise. We can control the amplitude if you think it's too much. Maybe 0.6 would be enough. Not really. So we should normalize this as well. Okay. If we don't normalize it, what's going to happen is we'll have different lengths, and that's going to be, instead of controlling the direction, we would also be controlling the speed of this. So if you want to do that, you can just create a parameter that's going to be the max speed or speed. And this is going to be multiplying the vector that we had. Right now the speed is at 0. At 1 we'll get exactly what we have. If we increase this to 2, we get twice as much speed. But now the difference is that when we generate our particles, they're going to go in all different kinds of directions. And there's a pattern to them that we can't really see, but if we go here, or where yet, the type of variation that's happening on the normals is this. It's going to be changing through time. The speed at which it changes is affected by the frequency, of course, of the anti-aliased noise. We can expose these parameters, but right now they're all being exported. All the particles are having all these different directions, but they have pretty much the same speed. What we can do is create a different noise to give them different speeds as well. So let's say we could create another anti-aliased noise. This one would have a 1D scale. We can change to apply an offset, something like this. Let's say the amplitude can be this, and then we would kind of multiply this here as well, and that way we have different values. Let's just check the range of value that's returned by the anti-aliased noise. Click the help here, and if I'm not mistaken, it's going to be from minus 0.5 to 5. That's why we have to 0.5. So we'll just do a fit range. And the idea is, if the value that's coming out is from minus 0.5 to 0.5, we apply fit range, say that the values are coming from minus 0.5 to 0.5, and we remap them to 0 to 1. And that way we don't have things going all the way to the back, but we will have some different velocities going on. And here on the noise, I'm going to say that the frequency is kind of half of this in terms of the time, how fast it changes. And we should see some nice variations of the length as well. If I increase the speed parameter to 4, it should be clearer that we now have ones that are really short, like this one, and some that are really long. And this is going to give us some good variations in terms of direction. Of course, the more points you have, the more detail we'll be able to see. Let's say twice as many. Yeah, it gives us some nice shapes. We can adjust here I'm going to make the frequency a bit higher so we have a bit more shapes. Not in time, I don't want it to change faster, maybe even slower, so that it kind of has, yeah. And here maybe increase this to 4 by 4 by 2. Yeah, let's see how this looks emitting particles. Okay, and we can, when you have a lot of particles, a lot of times it's easier to display them as pixels. So I'm gonna hit D, geometry, just make sure that instead of points we use pixels. And we can go to our pop network and increase the number of particles here, maybe 10 times. And that way we'll be able to see the patterns, okay? Some interesting patterns being generated from the way we're exporting these. And if you think the directions are just too wild, if you want them more still facing forward, we can kind of multiply the how much the noise is actually being applied to it. So if we go here to our pop network, nope. If we go here to our point pop, we can establish a limit of how we can kind of multiply this a bit. So we can, let me just grab this. So this is the random vector generated by the noise that's being added to our current normal direction, which is just aligned with the x-axis, so just facing this direction. And if we want this to contribute less to the final direction, we can have a parameter and to apply a multiply to this. And this parameter is going to be random or noise dear mult. And we can say direction noise multiplier. And that way we can control, let's say we want full contribution or zero contribution. It just means they're going to come straight. We only have variation on the speed. If you say 0.2, then we'll have variation on the sourcing as well. And you get this interesting type of effect. Okay, and this is just sourcing. Okay, the way you shape your initial velocity for emitting particles is really important for you to get an interesting result. Okay, as we can inherit the same way we can inherit velocity, you can do stuff like, let's go here to the grid, and let's increase the number of points yet a bit more. Let's say 50 by 50. And what we can do, I'm going to hit W. And another interesting operator that you have is attribute from map. We should have some UVs on this, so I'm just going to apply a UV texture. It's going to be orthographic projection. I want it along the x-axis. You can check your UVs by hitting spacebar 5, and that's it. And we can apply an attribute from map. And instead of using this texture, we can kind of choose one that's called mandrill.pic, I guess. Okay, it's this image. And you can use that to affect the colors of your particles as well. Let me disable the grid. Maybe increase the density here even a bit more. Let's say instead of, okay, and you'll get that color variation coming from the map and being inherited as well